Hello friends, in this video we are going to discuss about magnetic force between two parallel conductors, right? Parallel current carrying conductors, and this is my Insta ID. If you want to follow me on Insta, then you can follow me. Okay, so before we start, please subscribe the channel, help me to grow my channel, inspire me to create new contents for you. So now let's start the topic. So magnetic force between two parallel conductors, right, carrying current. So now let us consider two wires, W1 and W2. So in one wire W1, this is the current I carrying in this direction, and due to which magnetic field, if you apply the right hand thumb rule, thumb will be pointing towards this direction in the along the direction of current, and remaining fingers will be warped around it in this direction, that will be into the page, so that is represented by cross, right? And let us consider the current. We are considering the case of current flows in opposite direction. There will be two cases, currents if currents in same direction and opposite direction. First, let us discuss about the case of opposite direction current, right? So here I2 is the current carried by W2, and magnetic field due to this W2 is given by this cross. So if you apply that again, right hand thumb rule, then if thumb point towards this I2, then remaining fingers will warp around the conductor in this direction, so that is also into the page. So now let me write what I have considered here. Let us consider two parallel conductors, W1 and W2, carrying current I1 and I2 respectively. I1 and I2 in opposite direction. I have considered in opposite direction, and these two conductors are separated by a distance d, suppose, right? Let dl be a very small length element in the wire W2. So this cross is the field due to W1 directed inward, that is perpendicular to the plane, and this represents, suppose, the field direct due to W2 inward, directed inward, perpendicular to the plane. So now you see the magnetic force. We know that the magnetic force due to W1 at dl, that means magnetic force, I have taken this dl element, length element dl, which is let us suppose the vector dl directed in the direction of I2, let me consider that way, and magnetic field due to a wire current carrying I1 is given by this is known to us. Okay, so this is known to us, and it's perpendicular to the plane of the diagram and directed inward, right? So the magnitude magnetic field at dl, magnetic force, not field, magnetic force at dl, at the portion dl, that gonna be given by I2 in dl cross b. That means you see here, if we have a magnetic field in this direction, that is into the page, that is going into the screen of your device, assume that way, and this is a current carrying conductor I, and it's conductor, it's carry current I, suppose, and its length is suppose L, then force on, if this is the magnetic field B, and then force on this is given by force I L cross B. So using this we can obtain the force on dl as this. So what gonna be its magnitude? So this is suppose 1, I have taken this one as equation number 1, right? And its magnitude will be given by I2. So here we are going to find a force experienced by W2 when it is kept in this magnetic field due to W1, produced due to W1, and then here W2 carries current I2, so that's why it's gonna experience this force. And here I have used equation number 1, right? Using equation number 1, so here I have used this value here, okay. So and it implies this expression here, and this is the force per unit length on W2. Now you see this dl cross B, so here this is the direction of B, and dl I have taken dl in the direction of I2, so this is the dl, and so this is the direction of B. Now you see, if you use your right hand, then if you curl your fingers, first point the fingers of your right hand along DL, then curl it in the direction of magnetic field, then your thumb of your right hand gonna be pointing towards right side, so that force on W2 will be towards right side, right? Similarly, same amount of force will be experienced by W1 but in opposite direction, okay, if you analyze the force, direction of force, okay. So hope you have understood this. So here you see, if you consider this portion, now this is the direction which is perpendicular to the screen of the device where you watching the video, and this is the magnetic field V, and this is the direction of dl vector. Then take the if you point the fingers, all the fingers along this direction of dl, then curl the fingers along the direction of the magnetic field, that is into the page, imagine that way, then your thumb will be pointing in this direction. You may check yourself, okay, right? Okay, and now consider the case of W1. In this case, the direction of current is in this direction, so then if you apply the same process, then force will be pointing in this direction. So we have understood this. So now you see, so what we're gonna have here, that has the direction away from the W1, okay. The force on W2 is away from W1, similarly force on W1 will be away from W2, so they will repel if currents follow, if the currents in the wires are in opposite direction, they're gonna repel each other, right? So magnitude of the force on W2 of length, suppose L, let us consider the length of the wire is length of its wire be L. Then here you see, for DL we have got a force DF for the length DL, right? For the length DL. So what will be the force if the length is L? Then the force will be given by F is equal to this, mu naught I1 I2 by 2D into L, right? And same force will be, this force will be experienced by W1 as well, okay, but in opposite direction, okay. So, and let me tell you that if I1 and I2 are in same direction, then they're gonna attract each other, okay. Conductors gonna attract each other, right? So hope you have understood this. So but here in case of opposite direction, if direction is opposite direction, then they're gonna repel, okay, then they're gonna repel each other. So hope you have understood this. Now you see, and mention one more thing, what is mu naught here? Mu naught is nothing but permeability of free space, permeability of free space. Okay, permeability of free space, this is a constant. Okay, so let me explain about the direction of the forces. So here you see, if these two are the parallel conductors and the current in these two are in opposite direction, then force will be in opposite direction. They're gonna repel each other, right? They're gonna repel each other, and the current flows through these wires, suppose in same direction, then they're gonna attract each other, right? That is the concept. So hope you have understood, and if you like my video, please hit the thumbs up button and share with your friends. Inspire me to create new contents for you, help me to grow my channel. So thank you for watching. See you in the next video.